If you could step into a machine today and set the coordinates for any point in history, where would you go? Pop culture makes this look incredibly easy. You punch a date into a dashboard, pull a lever, and instantly vanish into the past. But the physics of our universe suggests a much more difficult path. In our everyday experience, time is a strict one-way street, moving continuously forward. To understand how we might change that, we have to look at time as a physical dimension. Think about a cardboard box. To exist in the real world, it needs length, width, and height. But it also needs a fourth measurement, duration. It has to occupy a specific when just as much as a specific where. Once we treat time as a physical dimension, a real space that objects occupy, traveling through it becomes a navigation problem. Much like sailing across an ocean, you just need to know how the currents work. For centuries, science operated under a strict assumption. As you see in this grid, we believe time was a rigid, universal clock that ticked at the exact same pace for everyone, everywhere in the universe. Then, Albert Einstein looked at the math and realized that assumption was wrong. He proved that time is flexible. It stretches and compresses depending on where you are and how fast you are moving. This realization, that the universe is a flexible fabric called spacetime, gave scientists a starting point they needed to search for actual paths through time. To see how this works in practice, we have to leave Earth. Navigating into the future requires the most extreme environments in the universe. Step 1 of our instruction manual is to find a source of extreme gravity. This diagram shows a flat grid representing spacetime. Notice how a massive, dense object placed on the grid actually bends and stretches the fabric downward. Step 2 is to wait. Because spacetime is stretching around that massive object, time itself is stretching. For anyone standing deep inside that curve, extreme gravity acts like a brake on their personal timeline, while time for everyone further away keeps racing forward. Step 3 is the return journey. If you park your ship near a black hole for what feels to you like exactly 1 year, you can return to Earth to find that an entire century has passed back home. You've reached the future by using gravity to slow down your own clock, while the rest of the universe sped by. Traveling forward is a clear matter of navigation, but turning around and trying to travel backward introduces immense structural roadblocks. Let's look at this diagram of a family tree to illustrate a famous problem called the grandfather paradox. If you travel backward and accidentally prevent your ancestors from meeting, you erase the connections that lead to your own birth. This creates a mathematical error the universe cannot process. You cannot travel into the past if you were never born to build the time machine in the first place. The only theoretical workaround physicists have found for moving backward involves wormholes. These act as cosmic shortcuts, folding spacetime to create a physical bridge between two distinct points in history. However, wormholes currently only exist as complex math equations on classroom blackboards. We have never observed one in physical reality. While traveling into the future is a matter of engineering, reaching the past requires us to find a way to bypass the core logic of cause and effect. So, if the math for future travel checks out, why aren't we packing our bags for the year 3000 right now? We have a few technological milestones to hit first. Number 1, we must master advanced propulsion systems capable of pushing spacecraft to speeds approaching the speed of light. Number 2, we need to invent new materials. A human body requires heavy shielding to survive the intense gravitational forces that slow down time. Number 3, we have to harness energy at a stellar scale, enough power to physically bend the fabric of the universe ourselves. The laws of physics permit us to travel forward. Our current challenge is building the tools powerful enough to do it. But we don't have to wait centuries to see this science in action. Humans have already crossed the threshold into time travel, right here in observable reality. When astronauts travel at high speeds in orbit, they experience time slightly differently than we do on the ground. When they return to Earth, they have technically traveled a tiny fraction of a second into our future. Every one of us is already a time traveler, moving steadily down a one-way river of time. We don't need to invent time travel from scratch. The universe has already provided the physics. Now we just need to build a faster ship.